class. This is my presentation for this week's library research assignment. My topic was perimeter and area, polygons and quadrilaterals. My name is Ryan Hughes, and we're going to go ahead and jump right in. In this presentation, I will be defining the terms used in perimeter and area and polygons and quadrilaterals. We'll be presented with some example problems and uses of the formula in order to find perimeter area and quadrilaterals and polygons. You'll also be presented with historical facts of perimeter and area. I will give you a use of perimeter and area in 2 full cell careers. Then of course we'll have my references page and my go-to training proof. Starting off with the definitions, perimeter is the distance around a figure, in this case polygons and quadrilaterals. Area is the number of square units that can be enclosed within a figure or a region. A polygon is a two-dimensional figure formed by connecting line segments. A quadrilateral is a four-sided polygon. Some examples of quadrilaterals: rectangle of 4 sides and 4 right angles, square, which is a rectangle with 4 equal sides, a trapezoid, a quadrilateral with a pair of parallel sides. Moving on, finding perimeter, we use the formula 2 width plus 2 length, or in the case of a square, we'd use the formula 4L, since all sides in a square are equal. The length in this case and the width is 1.5 inches. So we plug that into our formula for length. 4 times 1.5 equals 6. And we come up with a perimeter of 6 inches. Moving on to area, we use our formula length times width. The length in this case is 1.5 inches. The width being 0.5 inches. Plug that into our formula. Length times width equals 1.5 times 0.5. And we get a grand total of 0.75 inches squared. Now the reason we use squared in area goes back to the definition. As we said, area is finding the amount of square units in a figure. So finding square units, it just shows how many square units we could fit. So in this case, we could fit 0.75 squared units, or squared inches. Okay, going on to some use in full cell careers. First career I chose was show production. In show production, you would need to know the area of the stage in order to ensure that all the equipment and performers will fit comfortably onto the stage. So we jump right in. I built this chart here that kind of gives us a little layout of the show. The blue box representing the stage, which is 16 by 10 feet. The red boxes identifying the speakers, which are 5 by 5 feet. The yellow box identifying the amount of space the drums will take up. The purple box representing the stage lights. And the green boxes representing the amount of area that each musician would like to comfortably perform. So first thing we must do is identify the areas of the stage. So doing that, we use our formula area equals length times width, which would equal 16 by 10, which would equal 160 feet squared. Second, the area of all the equipment must be identified and then added. So the area of the speakers, 5 by 5, so we do length times width on that as well. 5 times 5 was 25, and since there was 4 speakers, we would multiply that by 4 to get a grand total of 100 squared feet. The drums area, 8 by 4, 8 times 4 equals 24, so their area is going to be a grand total of 24 square feet. Stage lights, 10 by 2, 10 times 2 is going to give us a grand total of 20 feet squared. And then the musicians all felt comfortable performing in a 3 by 3 feet square, so we're going to go ahead, multiply 3 by 3, and since there's 3 musicians, not including the drummer, which has already been accounted for, we're going to take our formula length times width 3 by 3, which would equal 9, and multiply it by 3 for each musician, and getting a grand total of 27 feet squared. We would then add all those together to get a grand total of 171 feet squared. After that, we come to realize that 171 feet squared is greater than 160 feet squared, and therefore the stages would not adequately fit all of the first off needs of the band. So in order to play this venue, they might want to drop a speaker or two. Maybe just play the show with 2 speakers in order to fit everything on the stage. Moving on to our next in the field, we use the subject of graphic design as a wholesale career. In graphic design, a client might request a graphic that borders a door, which is printed on a special material. It is your job to know the perimeter of this door to place the order for the correct amount of special material so that it fits properly around the door. So we're going to use our perimeter formula here. 2 length plus 2 width. Go ahead and plug in our numbers here. So we have the length of 7 and the width of 3, so we're going to go ahead and do P equals 2 times 7 plus 2 times 3. Simplified, P equals 14 plus 6. Then finally, we would get a grand total of 20 feet. So when going to the printing press, or whoever would be printing this graphic, we would request an order for 20 feet of the special material. For historical facts about perimeter and area and polygons are as listed. Our first uses of mathematics, including perimeter and area, came from ancient Egyptians and Babylonians. This was about 3000 BC, and the Egyptians used perimeter and area formulas in order to build their pyramids, as well as the Babylonians in order to build some of their structures around their cities. 300 BC, Euclid writes the Elements, which is where we begin to see more algebra mixed in with geometry. This is crucial to perimeter and area because if we were working with a square where we didn't need to know the side, or a side was not provided, or 2 sides were not provided, we'd need to use an algebraic equation in order to help find and solve the missing sides and lengths, widths, so forth and so on. Persians used perimeter and area formulas to construct mosaics. If you're not familiar with mosaics, mosaics are works of art usually made of tile or sometimes glass and squares, and it's actually a really good example of using area and perimeter. In 1957, Van Hal came up with his model to help students better understand perimeter, area, and other geometry. Now this is crucial because it gives us our future generations and the generations of now the advancements we need to proceed with the teachings of geometry for everyone in the world and everyone to come in the world. My references are as follows. You will notice on my references that they are actually numbered to the historical facts. The first one was Draco's M, Babylonian Mathematics, and that was actually retrieved from the internet, www.math.tamu.edu. Number 2 was a historical angle that was retrieved from EBSCOhost in the Full Sail Library. Number 3 is the comparison of NCERT and PSEB geometry textbooks on the basis of Van Hyl's level of thinking in geometry, and that was also retrieved from EBSCOhost in the Full Sail Library. Number 4 is a brief history on non-Euclid geometry, and that was retrieved from EBSCOhost in the Full Sail Library. Number 5 was our textbook, and that's where I retrieved all the formulas from for my examples, and that was retrieved from alex.com. Here's my go-through training session videos. Unfortunately, I was only able to make it 2 due to my work schedule. But that pretty much concludes my presentation and my video, so I hope you enjoyed, and I hope everyone gets a little excited about math after this. Okay, well, thank you.